Hello guys, we want to start lecture 34. In this lecture, I'm going to talk about boundary conditions. Then we talk about initial conditions, and at the end we talk about boundary value problems. First, we start boundary condition or BC. In fact, boundary conditions in a system identify condition of the system in the boundaries. For example, if you look at here, we have a fixed bar here or beam structure here. For example, if I assume that we have x-axis here and I define u of x and t as deflection of the beam structure. So in fact, u of x and t here is deflection of the beam. So you can see that at this point, which is 0, here length of the beam is L, so here is L, here is 0. So you can see that, for example, u at 0 and t in one boundary is always equal to 0. Why? Because we don't have any deflection at the boundaries at x equal to 0, or even at x equal to L. So we have u of L and t is equal to 0. So it's another boundary condition. So we can have boundary condition for the rod and heat equation as well. But before starting to talk about heat equation, I want to categorize boundary conditions in the three categories. So in general, for the heat equation, wave equation, and Laplace equation that we're going to talk about them in this chapter, there are three types of boundary condition. The first type of boundary condition, it's called Dirichlet boundary condition. So it's the first type, and they are in the form of U. So we call it Dirichlet condition. For example, for the case of fixed beam, so we have Dirichlet condition. So for example, it's u of 0 and t is equal to 0, or u of L and t is equal to 0 because the beam is fixed at x equal to 0 and x equal to L. So you can see that here the boundary condition is in the form of u. As a result, this condition is Dirichlet condition. So we can have the same for rod and for heat equation. So for this rod, the Dirichlet condition is, for this rod, u of x and t, it's heat equation, it's temperature equation. So heat or temperature function. For Dirichlet boundary condition, for example, we can say that temperature, it's just an example, at x equal to 0 or at the beginning of the rod, it's equal to, let's say, a constant, u0. Or we can say that temperature at L or at the end of the rod is equal to, for example, 0. Again, we are representing the boundary condition in terms of u. As a result, we are talking about Dirichlet boundary condition. The second type of boundary condition that we have is Newman condition. So for Newman condition, the boundary condition is in the form of derivative of u with respect to n, which is a normal derivative. And in this case, we call it Newman condition. For example, for the fixed beam, the second boundary condition or Newman condition, we know that in the fixed beam, the slope of deflection at the beginning and at the x equal to L, they're equal to 0. So slope is the derivative of u with respect to x. At x equal to 0 is equal to 0. So here you can see that we have derivative of u with respect to x. As a result, this boundary condition is Newman condition. And we have derivative of u with respect to x at x equal to L is equal to 0 because slope of deflection is equal to 0. So we have two Newman conditions for the fixed beam. If you want to find Newman conditions for the rod and for heat equation, so we have second type of boundary condition. For example, we can say that derivative of u with respect to x at x equal to 0 is equal to 0, or derivative of u with respect to x at x equal to L is equal to 0. So what does it mean? Derivative of u with respect to x in fact is heat flow. If derivative of u with respect to x, for example, at x equal to 0 is equal to 0, it means that at x equal to 0 we don't have any heat flow, so it means that the rod is insulated at x equal to 0. So I can say that if derivative of u with respect to x at x equal to 0 or any other point is equal to 0, then the rod is insulated. At x equal to 0. So as a result, if in a problem, the problem says that you have a rod and is insulated at x equal to 0, so you have to know that it means that the boundary condition is derivative of u with respect to x at x equal to 0, it's equal to 0. So here the second boundary condition. Now you want to talk about the third boundary condition. The third boundary condition is called Robin condition. So it's in this form: derivative of u with respect to n, which is the normal derivative, plus h times u. So in this case, h is a constant. H is constant. So we call this condition Robin condition. For example, for the rod and for the heat equation, or Robin condition, we can say that, for example, derivative of u with respect to x at x equal to L, it's equal to minus h times u of L and T minus um. So in this case, u of L and T is temperature at x equal to L. U of M is temperature of medium. And H is a constant. So what does this boundary condition say? It says that the heat flow at x equal to L, which is derivative of u with respect to x at x equal to L, is proportional with the difference of a temperature at x equal to L and temperature of the medium. So it's a boundary condition, and this boundary condition is called Robin boundary condition. So I say again, the heat flow at x equal to L is proportional with the difference of temperature at the end of the rod and temperature of the medium. So we have these three types of boundary conditions in this chapter. Now we know about boundary condition. I want to talk about initial conditions. Initial conditions identify condition of the system at t equal to 0. For example, for this rod, we can say that temperature of rod at t equal to 0, it's equal to Fx. What does it mean? It means that at t equal to 0, let's say I say fx is equal to x, or any function. So imagine we say that temperature of the rod at t equal to 0 is like x. So what does it mean? It means that at point x equal to 0, so here we have x-axis, temperature is 0. When you go further, the temperature changes linearly, for example like this. So in fact we are talking about condition of the system at t equal to 0. Or for example, we can say derivative of u with respect to t at t equal to 0 is equal to gx. It's another function, it can be an arbitrary function. Again, we are talking about condition of the system at t equal to 0. In fact, it means we are talking about initial condition of the system. So it's about initial condition. Now we want to talk about boundary value problems. Boundary value problems, in fact, partial differential equation subject of boundary condition and initial conditions. So they are called boundary value problems. For example, here it's just an example. So we have a partial differential equation. It's a squared times second derivative of u with respect to x is equal to second derivative of u with respect to t. It's not heat equation because we know and the general form of heat equation. In heat equation, we have second derivative of u with respect to x is equal to derivative of u with respect to t. This equation is just a partial differential equation. We're going to talk about it later. But it's a boundary value problem. Why? Because we have a boundary condition, as you can see here. We have a partial differential equation, as you can see here. We have boundary condition. Boundary conditions says that u of 0 and t is equal to 0, u of L and t is equal to 0, and we have initial condition as well. So we have u of x at time equal to 0 is fx, and we have derivative of u with respect to t at t equal to 0, it's equal to gx. So it's one boundary value problem. Or another example, here we have second derivative of u with respect to x plus second derivative of u with respect to y is equal to 0. So again, we have a partial differential equation which is subject of boundary condition and initial condition. So boundary condition says that the derivative of u with respect to x is equal to 0. The derivative of u with respect to x at x equal to 0 is equal to 0. Derivative of u with respect to x at x equal to a is equal to 0. And initial condition says that u of x and 0 is equal to 0. Or u of x and b is equal to fx. So boundary value problem can be homogeneous and can be non-homogeneous. In fact, BVP or boundary value problem is homogeneous if partial differential equation and boundary conditions are homogeneous. So now we know boundary value problems, we know initial conditions, boundary conditions, and we know heat equation. As a result, we can solve the heat equation. In the next lecture, we talk about the solution of heat equation. In fact, heat equation is a boundary value problems because we have partial differential equation, we have boundary condition, and we have initial condition.